Okay, good evening or good afternoon or whatever it is, ladies and gentlemen. I hope you're having a great time at ESOF, and welcome to this evening's plenary. It gives me great pleasure to introduce Cedric Villani. I know that many of you will know him already, so perhaps for some of you, he won't need much of an introduction, so I will be brief. He is the director of the Henri Poincaré Institute in Paris. He is an amazing mathematician, as evidenced by the fact that he has won the Fields Medal in 2010, plus many other prizes and awards. He has written a hugely successful book called Living Theorem, in which he describes his life as a mathematician and what it's like to be a mathematician. And as I said, it's been very hugely popular. He also spends lots of his time going into schools and popularizing maths. So it's amazing, really, I think, that we have someone like him that's dedicated so much time to popularizing mathematics. So this evening, after Cedric's talk, we won't be having a roving mic for you to ask questions. So if you do have some questions, please can you use the hashtag ESOF2014. I know that lots of you have been using that already. So if you have any questions, tweet those to that hashtag, and they will collect them for me, and I can ask you some questions on your behalf. So without further ado, let me welcome Cedric Villani.
Okay, thank you very much for that great introduction. It's a real pleasure to be here. It's a real pleasure to be part of this wonderful scientific fest, which is ESOF. Today, I will talk about mathematics and the ongoing efforts of mathematicians to predict the future of some simple systems. Prediction is so hard. Even when the systems have obeyed rules which we know and which are sometimes extremely simple, it may be extremely tough to get it right what will happen. To illustrate this kind of complexity, let us start with a short movie. What you will see in the movie is, yes, this is a problem with my haircut. You know, it's always pleasant when you are resting and there are people taking care of you, like the haircut, the makeup, whatever, and so forth. So what you will see is a bunch of what happens when you have a bunch of stars moving, evolving, just under the laws of gravity, which Newton discovered in the 17th century. Just one simple rule and such a complicated motion. Let us see the movie, please. So time scales is very large, like millions, billions of years. Look at these crazily complicated patterns. Just one rule, gravity, and that's all. We know the equations, still it's very difficult to say anything intelligent in front of this. You know, as a scientist, you want to describe. How are we going to describe this? We want to understand. What the hell is there to understand here? We want to predict what will occur. How do I know? You see the difficulty. It's not because you know the equation that you can predict. Let's see also for fun how it is when two galaxies collide. Look what joyful event. Some people, we say that in 2 billion years, this is what will occur to our galaxy, meeting the Andromeda galaxy. NASA has done computations about it, and other institutions have done it. Look, just one rule, the Newton interaction. So that's it for the movie, and let's keep that in mind when we go for the rest of the talk. Let us please go to the bulk of the talk. So I'll talk about long-time behavior of gases, plasmas, galaxies, a bit of the theories, many mysteries, and evoke some of the efforts done by mathematicians over the past centuries to put order into this and to understand some of the principles behind. Why do we want to predict? Well, there are many possible motivations. Maybe you want to know if our galaxy will one day meet the Andromeda galaxy, even if you will not be there to see. You want also to understand which, for instance, in a physical system, are the observations that you will be able to see in practice. And sometimes this is associated, often this is associated to the idea of a stable behavior in the long time. What is stable, you will observe. What is unstable, you will not observe often. Also, most of the realistic systems, there is no formula for the solution. So having the long time behavior, what happens in the long run, is already something. And let us say that even if you're focusing on just the long time behavior, it may be extremely difficult even for classical systems. And in my talk, there will always only be classical systems. So no quantum, no relativity, just the basic laws of mechanics. The oldest mathematical problem set with these is the stability of the solar system. What is it? Let's recall. First, you all recall the Kepler's laws. We learned this in high schools. Around 1600, we understand that planets are elliptic trajectories around the sun, and that with the three Kepler laws, we can compute the velocity of the planet in terms of a few parameters of the ellipse. And in this picture, these are orbits which are really close, so that the motion is closed and forever. However, it was understood years later that this was only an approximation. And it is only 1684 that Newton publishes the equations which have his name and which were the standard for the study of the galactic dynamics for the centuries to come. We still use the Newton equations, except if the phenomena are very, very fast, so that you need to use relativity, or if the scale is extremely large, so that there are anomalies which lead people to speculate about possibility of dark matter or other things. But apart from that, Newton's equations are still the standard. I wrote here the Newton equations. I don't expect, I will not explain in detail what you do with them. But let us just say that these are equations for a bunch of particles moving. This can be a bunch of planets. Let's call capital N the number of planets. And when there are just two bodies, say one planet and the sun, or two planets, we can integrate, we can solve the equation and recover the discovery of Kepler that the motion is an ellipse and that the sun, if it is the planet and the sun, occupies one of the focal points of this ellipse. When n is bigger than 2, you cannot solve, you cannot integrate the equation, so what to do? And the question of Newton was, is the solar system stable? If I wait for very, very long, can it be completely destroyed so that it will not look like the one we know today? Or on the contrary, will it for billions and billions of years remain the same as we know it? And Newton famously thought that on the basis of the equations, you cannot explain the stability of the solar system, so that you need to invoke a divine intervention to impose the stability of the solar system. It can be set in more general terms. Take a bunch of particles with an interaction potential between them, a force of attraction or repulsion, not necessarily gravity. What do the trajectories of that system look like as the time becomes very, very, very large? So, as soon as you know what the differential equation is and you know that you can solve it, that there exists a solution, the problem makes sense, but is still extremely hard to solve. In the case of the solar system, the bodies are not any bodies. One is much larger than the others, of course. The sun heats up something like 99.9% of the total mass of the solar system. Earth is just some kind of tiny perturbation, like a bit of dust in this whole picture. So, of course, you'd like to think that all the planets and the influence of the planets on each other, this is what destroys the Kepler system in the long time. This is just a perturbation when it comes to the trajectories of the Earth. The Earth interacts with the Sun, that's the main effect, and then there's a perturbation due to the action of all the other planets, like Jupiter, but this is much smaller. The size of this perturbation will be about like 1,000th, because that's the ratio approximately of the masses of the planets to the mass of the Sun. What Newton was worried about is that even if epsilon is very small, if you wait for a large time inversely proportional to epsilon, the accumulation of errors could be a big, big trouble. It's like if your bank account loses 1,000th of its value every day. On one day, it's nothing, but on 1,000 days, it is a big trouble. And of course, he was worried by that because this would suggest that the solar system is unstable over a time scale of the order of the millennium, which he could not believe and we could never believe. Later, however, at the end of the 18th century, wonderful mathematicians proved that the typical time scale, and this you obtain by really analyzing the equations, is not 1 over epsilon, is 1 over epsilon squared that you have to wait. So that the typical stability from the equations is at least of the order of the million years, not the millennium. After that, of course, people could wonder about what comes in the very long run, what happens if you wait for 1 billion years. And we have to wait the end of the 19th century until somebody really tackles this question, and this was the work of Henri Poincaré. After a very chaotic process, so to speak, and he thought he could prove the stability forever, he proved that there is a mechanism that can generate long-time instability, and he showed that it's impossible in practice to determine whether it's stable or unstable unless you have infinite precision on the positions of the planets, which of course you never have. This was a preliminary precursor to what is now called chaos theory. 15 years later, Kolmogorov shook the whole scientific world by showing that even if there was a possibility of instability, if the perturbation is very, very small, then the system of the gravitating bodies should be most likely stable. That is, if you look at statistical initial positions, most of the time it should lead to stability forever, and only with small probability it should be unstable. And from that moment, people believed that the solar system was in fact stable. This was in the 1950s. And then it was again shaken, the opinion of scientists on this, in the 80s when people like Laskar or Tremaine proved chaotic behavior on computer simulations in the long run and showed that there is a possibility of catastrophes in the long run, say on the time scale of the billion years. So you see how just one question, the stability of the solar system, led to 1, 2, 3, 4 scientific revolutions, so to speak, 4 revolutions in the study of classical mechanics, each of which had important consequences much beyond classical mechanics, because they were evidence, they were displaying new phenomena which were useful then in other fields of mathematics and physics. One paradigm that emerged from all these studies is the idea of ergodicity, pioneered by Boltzmann in the 19th century, then in germ in the Poincaré works, and then developed by people like Birkhoff. The idea that if a system is ergodic, it's a system that is as disordered as can be, visits everything that is admissible. So if you want to have information about the typical position of this system, you first determine which is the list of all the states which are achievable after you take into account laws of motion and restrictions which prevent the system to go into this or that state. And then you look at the behavior of the system averaging over time. Let's say, which is the typical place where the system will be when I look at a typical time. If ergodicity is true, it will be the same as the typical state in the space of all possible states, and you can use some probability measure to say in which sense it will be typical. For a long time, people thought that ergodicity was a kind of general rule, and it has developed actually into a whole area of mathematics, ergodic theory. And it was a great shock when Kolmogorov, whom I already mentioned, and Arnold and Moser showed by looking at the example of an integrable system which is perturbed, like in our case, the solar system, if you don't take into account the interactions of the planets between themselves, it is integrable, as Kepler knew. But if you perturb it by a tiny interaction, then with high probability, the system will remain stable for all times, and that is in contradiction with the idea of ergodicity. So with these two slides, the one just before and this one, I have summarized something like 1 century of research in the emergence of two paradigms, the idea that sometimes a system can be very, very disordered and visit everything that is allowed, and the idea that sometimes it will not visit everything that is allowed, but remain stable. Do these theories apply to the real world? That's a big question. And in particular, here you see some issues about what mathematics is. In large part, mathematics is a study of some abstract reflection of the world. In large part, it's also predicting things in a quantitative way. But in this case, even though ergodicity and Kolmogorov-Arnold-Moser theory have been a revolution, both in mathematics and in physics, none of these theories applies often. It's worse. There are extremely few real systems which are known to be ergodic, and many systems which are known to not be ergodic. The example which Boltzmann considered, take a system of billiard balls in a periodic configuration. It was proven only last year by Simani, Hungarian specialist of this topic, that it is indeed ergodic. It took something like 150 years to prove this. And still the proof, for some reasons, is not the definite answer to the issue. Kolmogorov-Arnold-Moser theory almost never applies to real systems because it needs the perturbation to be so tiny that in practice it will not work. If Jupiter was of the size of a football ball, maybe of a soccer ball, then maybe it would apply. You see the kind of crazy orders that are needed. However, both theories have been a revolution, both for mathematicians and for physicists, which is a kind of epistemologic paradox, but also shows that the study of the reflection can be useful in changing your point of view, not only in making qualitative predictions. Now, what about the stability of a galaxy? Remember the movie we saw at the beginning. Remember, I told you stability of solar system was such a mess. And in the solar system, there are, 9 or 10 planets, that's all, and the sun. In a galaxy, you have maybe 100 billions of stars. What do you do with this? Looks crazy. But to study it, you will change the point of view. And this is part of the revolution, the word is not too strong, which occurred around the 2/3 of the 19th century when Maxwell and Boltzmann developed the idea that you can explain many complex phenomena occurring at our scale through statistics and simple microscopic laws. There was a major modeling advance, the Boltzmann equation describing the behavior of gases, A major mathematical advance, the notion of statistical entropy, a mathematical notion inspired from physics. Major physical advance, the notion of irreversibility. Why does time seem to flow always in the same direction? Why do things always go in the direction of more messy? This is part of the Boltzmann theory. And a major advance in the study of so-called partial differential equations in the way to understand large time limit of a statistical system. The outcomes of the revolution were enormous, in particular the explanation of Brownian motion, the evidence for atoms, this came in the beginning of the 20th century, and the idea that the world is made of equations on our scale, which are a reflection of the microscopic laws and the statistical nature of matter around us. This is of considerable importance because all our life is dictated by this statistical nature of our world. I will only mention it in the classical regime, but it has also been adapted to all kinds of physics. It was, let me insist, Aesop is a mixture of all sciences. It's good to recall that all sciences are interdependent. Sometimes we think of physics as using mathematics to solve problems, but in fact, very often it is also physics giving new tools and ideas to mathematicians. Some of the quotes which I gathered here show how strong was the influence of the physicists of that time, Boltzmann in particular, on some mathematicians, saying that they stand by Boltzmann's side in a debate, Hilbert mentioning Boltzmann's work as an inspiration in one of his famous problems, or Mark Katz, the great probabilist, saying that Boltzmann's book is one of the greatest books in the history of exact sciences and that the reader should consult it. If you want to study the long-time behavior, what happens in large time for a statistical system, then a galaxy, for instance, a new plan emerges. Instead of saying, okay, there are 100 billions of stars, so let's study this huge system of 100 billion equations, let us rather show that these particles have some kind of independence property, that this star and that star will interact very little, will not be correlated or almost, hardly be correlated. And this so-called chaos property will allow you to get a statistical equation replacing, in the limit when there are many, many particles, the original laws of gravity, for instance. And after you have this statistical equation, you let time become large, not before. And the idea is that there are so many particles that it will not look like a bunch of particles, but like a fluid. Remember, once again, the movie that we saw at the beginning of the talk, it looked like a kind of gas, not as individual particles. This was the birth of kinetic theory, in which you don't focus on particles, but on the statistics of particles, particle density in phase space. And the new unknown in that model is not the distributions of positions and velocities, is not the positions and velocities, but their statistical distribution. Which are the velocities which are more likely to occur, which are the ones less likely to occur, and so on. That's why it's called kinetic. It was very daring. In those days, for gas, existence of atoms was not proven. And so velocity of an atom could just be a meaningless concept. Think of this, how strange it is to see that the air around us, which looks so stable and at rest, is in fact made of billions of particles moving in all kinds of directions. And it was very daring to use these extra variables which are invisible and to do some averaging on them. And then the two main models which were developed from that, once again, I don't expect you to understand them, but it's good to show concretely what they are. These are partial differential equations. The one above is the Vlasov equation, which describes a gas in which particles interact through long-range interaction. And the one below is the Boltzmann equation describing a gas in which particles bump into each other so that it is just short-range interaction. You can think that Above, it would be a world in which all the interactions between people would be by cell phone. And the one below would be a world in which all interaction of people is by direct encounter. And these are different physics, different equations. And in real life, often it's a mixture of both. But one regime can be useful more than another. These equations are the two pillars of kinetic theory. If you're interested in rarefied gas dynamics, for instance, if you're an engineer in the field of planes and so on, then you need to know about the Boltzmann equation, especially if you are working in high altitude. If you're interested in galactic dynamics or in plasma dynamics, it will be the Vlasov equations, because the most important phenomena are long range, not short range. What happens with the long-time behavior of these equations? And they fought very hard. They thought and they fought very hard to understand this, these people from the 19th century on. The main insight came from Boltzmann's entropy. Let me explain this. This is a concept which is at the same time simple and deep. When you are looking at a macroscopic quantity, like when you're looking at some system like the gas around us, you can only make macroscopic measurements, like the pressure or the wind or the temperature. Each of these measurements is averaged over billions of particles. But you don't know which are the individual states of any of these particles. So there is a lot of uncertainty at the microscopic level. Let's call W this amount of uncertainty, the whole range of possibles. Boltzmann formula, S, the entropy, is K times the logarithm of W. Logarithm measures the size of the number, let's say. So this tells you about how large is the amount of uncertainty, how many digits you need to write it down. This formula is no less important than, say, Einstein's famous formula E is mc squared. I think it is, in fact, much more important because it dictates every single of our moments in our daily life. The formula appears on the grave of Boltzmann. Let's make a zoom, please, on the top. You see here, S is K log W. Actually, this picture was taken in Vienna. We can unzoom. This picture was taken in Vienna in 2006 for the anniversary of the tragic death of Boltzmann, and there was a big conference in Vienna. As a specialist of entropy, I was invited there to lecture. And I knew the grave of Boltzmann was in the central cemetery. So I go there, and it's a huge cemetery where many famous people are buried. So I tried to find my way. It was hopeless. Then I asked people sitting around if there is any map somewhere where we can know where the famous people are. And the guys told me, there is no map. Who are you looking for? I say, Boltzmann, thinking maybe they heard of him. And the answer was exactly, S is K log W. So this was an exemplification that this really is a magic formula, like a kind of password between people in cemeteries, people who know how much the formula is important. So entropy has a mysterious charm. You know, even the word makes for its success. Shannon, in the middle of the 20th century, rediscovered entropy and found that it was crucial in communication theory. We all use entropy when we transmit a message through cell phone because this is used to calibrate the channels through which the information has to go and the compression and so forth. And here is what Shannon says about him calling this quantity arising in his theory the entropy. I thought of calling it information, but the word was overly used, so I decided to call it uncertainty. You may think, how on earth can this guy hesitate between information and uncertainty? It seems to be the contrary of each other. It's just a question of point of view. The idea being that if something is a priori uncertain, you would get information by decoding the message. If, on the other hand, you already know in advance what will occur, then there is no point in decoding. You will get no information. For my student, I always use as an example, slightly, to be a bit funny, the example of the political speech. When the politician says something and you know in advance, depending on party, what will be the speech, then there is zero information involved. You should call it entropy, he said. So he discussed it with John von Neumann, Shannon. He had a better idea. You should call it entropy for two reasons. In first place, your uncertainty has been used in statistical mechanics under that name. So it already has a name. Well, that's good. And in second place, and more importantly, no one knows what entropy really is. So in a debate, you will always have the advantage. I think he was very wise, von Neumann, because the simple fact of calling it entropy makes it much more fascinating. This seems to be some kind of curse, meaning that we can never really understand the meaning of entropy, but with simple example, you will understand it easily. So let's go on to explain about the entropy in the form of a mathematical exercise. Imagine you have n particles, like it would be the particles in a gas, the molecules, let's say. And you can measure some quantity of those particles, maybe the energy, so put them into boxes. Say you have various levels of energy, and you give numbers to the boxes depending on the number of the value of the energy. And assume that you are observing some statistics, some frequencies. F1, the frequency of particles in box 1, F2, the frequency of particles in box 2, and so on. So let's call Nj the number of particles in the box J, and let's count the number of configurations such that the particles configuration will match the frequencies. This number of configuration corresponds to your uncertainty. Example, suppose that the frequency vector is made of just zeros, except there is a 1 in a certain position. And there is zero uncertainty. You know that all the particles are crammed into that single box, so the number of configurations possible is 1. But let's assume now that there are two non-zero frequencies. This is 3/4, this is 1/4, and maybe there are 8 particles, and it's a combinatorics exercise, the one you do at the end of high school. And the number of configurations is 8 factorial divided by 6 factorial, 2 factorial. In other words, the combinatorial coefficient, 8 choose 2. And more generally, if you put an arbitrary frequency vector, I put these numbers, for instance, this will correspond to certain numbers of particles in boxes, and you ask, which is the total number of possibilities to put these particles into the boxes? According to the prescribed frequencies, the solution of the combinatorial exercise is n factorial divided by the product of the nj factorials. That's some quantity you can compute. Now, that number, when you compute it, if n is large, it's a huge number. When you have huge number, we take logarithm. It makes them much smaller. If you take the logarithm and divide by n capital, when n becomes very, very large, this whole quantity approximates some finite, simple combination obtained from simple function obtained from the frequency fj's. This is the value of the entropy. And you see that in this way, it measures the amount of uncertainty that is left after we have observed the frequency vector. The uncertainty which is left at the level of the individual, so to say, the free will that the particles have, putting themselves in this box or that box, provided that we still observe the prescribed configuration. This was an enormous progress of Boltzmann. Boltzmann interpreted the last quantity into this kind of formula, is the continuous version of the discrete formula I just wrote before, which now can be computed. An engineer, a physicist can compute this entropy thanks to Boltzmann. And Boltzmann proved, using the Boltzmann equation, that it can only increase with time with uncertainty if the gas is inside a box. This was an enormous conclusion. It shows that in a way, spontaneously, collisions imply that the disorder increases. Now we call this second principle of thermodynamics, but the beautiful thing is that Boltzmann understood it as a theorem, something that you can deduce from the equations. Boltzmann also showed that it decreases strictly unless the velocity statistics are very special, meaning Gaussian, the typical bell curve fluctuations which we see in many, many random phenomena. Entropy, to summarize what I said, measures the volume of microstates. Microstates, this is the microscopic state, associated to some degree of accuracy in the macroscopic observables to a given macroscopic configuration. This was the frequency vector. So entropy answers the question, how exceptional is the observed configuration? Does it come from just one possible configuration or many? Entropy is in the eye of the observer. It depends on the resolution that you have. If we were microscopic beings able to tell one atom from another, there would be no entropy, so to speak. Entropy measured on our scale is not the same as entropy measured on the scale of a bacteria, and is not the same as entropy measured on the scale of the Earth. In that way, it is very different from a quantity like energy, which exists independently of your observation technique. It is related to other famous notions of information or uncertainty. In particular, maybe some of you know that Yasha Sinha is the last winner of the Abel Prize, one of the most prestigious prizes in mathematics. He improved and developed on the notion of Boltzmann's entropy to devise what is known as the semi-Kolmogorov entropy, telling us about how difficult it is to predict the trajectories of a system or to describe them. The Kolmogorov complexity is another notion, let's say from theoretical computer science, which is there to tell us about how difficult it is to understand some phenomenon. Entropy was born from physical motivation, but then became a mathematical concept. You saw it arising in this talk as a solution of a combinatorial problem. And as such, it is not surprising that it acquired a life on its own, serving to solve many problems which are not related to gas theory, or sometimes even not related to physics. It played a crucial role in the work of another Abel laureate, Peter Lax, working on compressible fluid mechanics, information theory, as I said, statistical error theorems. Also, the maybe most striking mathematical result of John Nash, a result about the regularity of equations related to stochastic processes and heat diffusion, was based on entropy in a way that was extremely surprising. And also, certainly, many of you have heard about Perelman's proof of the Poincaré conjecture. This was the biggest mathematical news in the past 15 years, and this was in its time ranked as the most important discovery of the year. It was also based, among many other ingredients, on entropy, and it was a geometric problem, not a statistical problem, and so forth. Even in non-commutative geometry, where there is really zero statistical physics, apparently, Voiculescu managed to show that you can use entropy in a very effective way. This, once again, I insist, once some technique is inspired from another field, it can acquire a life on its own as a mathematical technique. How do we apply entropy to our problem of large-time behavior? Entropy allows to distinguish very strongly between the Vlasov and the Boltzmann equation. Remember, Vlasov equation is when all the particles are influenced at distance, like the stars. The influence of gravity is very much long range. And Boltzmann equation is when particles collide each other, like the gas, the air around us. And if we look at the properties of these equations, both have constant energy. Energy is conserved in the classical versions. But one has a constant entropy. The value of the entropy does not change in time. And this is a consequence of a theorem known as Liouville theorem. While the other one, as shown by Boltzmann, has an entropy which increases, so that things become always more and more messy, more and more disordered. As a consequence, the Boltzmann equation is time irreversible. It shows that there is an arrow of time in the behavior of the gas. If you look further to the fact that the Boltzmann equation has very few equilibria, only Gaussian equilibria, while the Vlasov equation has many, many equilibria. For instance, you take any profile of the velocity, it will be in equilibria. Looking at the left column or the right column, you get completely different ideas. On the right-hand side, it seems to be a natural consequence of all this, that the gas will always become Gaussian, and that this thing cannot be stopped, it's irreversible. And that's indeed what is observed, and that was the contribution of Boltzmann, and the idea that this is explained from the increase of entropy. So this was an enormous progress in terms of understanding the long-time behavior of statistical problems. On the contrary, if you look on the right-hand side, there is nothing that leads you to think that there is some definite behavior. Entropy is constant. There are so many equilibria that how to choose between them. And so it was thought for a long time that what stabilizes a system is entropy increase. And if you don't have entropy increase, the system can act in a very erratic way, and nothing special will occur. This idea was dominant idea between 1870 and 1940. And in the 1940s arrived another revolution in this understanding. By means of Lev Landau, one of the greatest physicists of the 20th century, Russian. And what Landau did is take the Vlasov equation, which is a nonlinear equation, replace it by a simplified linear version. This is called linearization, near some equilibrium, and show that for some very, very smooth, very gentle distributions, the force, the electric force, say if you are in a plasma, which is a gas of electrons, or the gravitational force, if you are looking at a galaxy, will damp to zero in the large time, showing that there is some stability, apparently, even if this system has constant entropy. This was a revolution. He even computed, in the case of plasmas, a rate of exponential decay, making a prediction that you could, in practice, in theory, check measuring the electric field. With a complicated formula, don't worry about what it is exactly, but you see it is a formula giving you exactly what should be the rate of exponential decay of the force. This was the start of many works about the long-time behavior of the Vlasov equations. It's one thing to know the equation, it's another thing to know how it behaves. Like it's one thing to know a certain person, it's another thing to understand how he or she will behave. The same for the Vlasov equation. And Landau was suggesting that perturbations in a plasma or in a galaxy may damp away spontaneously in an apparently irreversible way, even though we know the equation is reversible and the entropy is constant. There seems to be a paradox. Then there were much discussions about the long-time behavior of the Vlasov equation. In astrophysics, it is very much accepted that, for instance, statistical perturbations in the velocity distributions of the stars in the galaxy will spontaneously damp over a time scale which is rather short, much shorter than if it was due to entropy increase. This paradoxical behavior is called violent relaxation, and nobody really knows what it is, except that it is relaxation occurring faster than should be. It is fundamental if you want to understand why galaxies often seem to have velocities that are kind of at rest, apparently, like the forces seem to be, the gravitational force in the galaxy seems to be at rest, while if it was due to entropy increase, the age involved would be much, much longer than the age of the universe. There have been some statistical theories trying to understand this large time behavior of the Vlasov equation, but none of them is based on the dynamics. They just try to guess from possible equilibria. The only case so far in which we understand something is about this Landau damping in the perturbative regime. This is, once again, start from rest, make a small perturbation, and let it go. Is the linearization reasonable? Aha! Landau made this prediction by replacing the nonlinear equation by the linearized equation. Here, even if you don't understand the equation, the unknown is h, the perturbation. Here it appears just 1. This is a linear term. Just 1, this is linear. But if you look at the blue terms, it's a product here. H here, it's a quadratic term, so it's a nonlinear term. When we linearize, we replace this quadratic term by 0. And are we allowed to do this or not? Well, if it's very small, you know the square of something small is something much, much, much smaller, so it should be negligible. Okay, true, true. But will it remain small in the long run? Actually, no. For instance, you can show that if you wait long enough, the term which you neglected in a certain sense becomes much larger than the other terms, apparently. It's the same kind of paradox as in the problem of Newton and the stability of solar systems, so to speak. It was observed by Backus already in 1960 that we are doing something here that seems to be wrong, and he has an argument seeming to destroy the validity of the linear theory. There are other arguments, which I will skip, which give you doubt about whether it's reasonable to linearize or not. There seems to be a logical contradiction in linearizing and looking at the long-time behavior. And physicists, mathematicians, various physicists and mathematicians have worked on this over the years and obtained contradictory insights. Together with Clément Mouot, former student of mine, we solved this problem in 2009, at least in the mathematical world. And we proved that for the nonlinear model, it is true that Landau damping does hold true, at least with very, very smooth, very gently varying periodic data. And we proved that, indeed, the force decays exponentially fast to 0. So the progress was to show that in the deductive line, you can do the linearization in this case, and the limit, the large time behavior, will still be valid. This was a huge work. Let me notice this was the first page of our article, the table of contents. Notice it's 180 pages long. All this to prove just one theorem. This is definitely not the longest paper in history, far from that. There are proofs that are even much longer than this. But reflect about this also, about the nature of mathematical sciences. We, or some of my colleagues, are ready to go through hundreds of pages of computations, sometimes just to prove one statement. But sometimes, how to choose whether the statement is right or wrong? Sometimes physical intuition is not enough. And that is one of the cases in which it was not enough. Some of the mathematical comments on these results, we also proved that the statistical distribution itself does converge in the mean. That is, if you forget about the fast oscillations and only keep the large-scale tendency in the velocity scale. We also showed, and that was something we did not expect, that a important key in the problem was regularity. How smooth distribution is. Let me note also that the proof has been simplified since then by Bedrosian, Masmoudi, and Mouot. It remains a very complicated proof, but still significantly simpler than the one we had. It's also in the order of things. For mathematicians, proofs do matter at least as much as the results themselves. And when you have a complicated proof, it will be simplified later. That's the general rule. If it is not simplified, this means that nobody is interested in your problem, and it's a bad sign. Physical comments, how do we solve the apparent contradiction between the persistence of the entropy and the apparent irreversibility? It is that all the information goes into the small velocity scales. This already had been guessed by physicists already a long time ago, even though you still find in some textbooks some wrong statements about that. And you will see this in the simulations here. This would be, say, the perturbation at some time in the velocity space, the statistics of the perturbation. At later time, see how much this oscillates. You cannot, in practice, keep track of all these oscillations. And that's why it appears as something which is kind of damped. In the same way as if you try to measure an electric current which oscillates very, very fast, your measure may be something that is completely flat. That's the same thing. And see how the energy can decay in an exponential way. This is a logarithmic plot for your system. Here, this is for a gravitational system. Here, this is for an electric system. I told you just a moment ago that the proof was at least as important as the result. One of the key insights, which we did not expect, was that there happens to be a tight link in the proof between three important paradoxes of modern classical physics. One I told you about is the Kolmogorov-Arnold-Moser theory about the stability of a solar system. The other is the Landau damping that we are discussing. And third was this plasma echo. And what we discovered is that the three phenomena are very much linked, and in the proof, the plasma echo phenomenon plays a crucial role. What is plasma echo? Plasma echo is another thing showing that classical systems can behave so strangely. Can we please zoom on this? Operator, can we? Yes, thank you very much. Look at this. Prepare your plasma. Think like a gas in which you separate the electrons from the rest. Measure the electric field. It is 0 if your plasma is at rest. Make a perturbation. Sorry. Make a perturbation. The electric field will go slowly to 0 again. Then send another pulse with a different frequency, and it will go again to 0. And then do nothing, and the plasma, after being kind of at rest, will do some echo. Spontaneously, the electric field will go up. This is called the echo. It shows that plasmas react a bit weirdly, sometimes with delay, and this delay plays an extremely important role in the proof of stability. This was unexpected, and of course, if you prove something using only expected tools, that's not good. You need to have some surprise coming in. So I think that's the end of this talk. Let me mention that I told you there is a link between Kolmogorov-Arnold-Moser theory and nonlinear Landau damping. Can we please unzoom? I did not explain you which is the link, but here this is a table which I wrote for a paper we wrote together with Clément for a physics review, in a plasma physics review, to explain which was the link between these two problems, which deal with very different physical situations, but happen to have links in the mathematical words and methods. And there is this correspondence, which you can see only in the mathematical world, and which gives you a new insight, a new way to look at the Landau damping problem. And let me also note that using these same kind of insights together with new tools of their own, Bedrosian and Masmoudi recently solved another problem of long-time behavior, which was standing for more than 100 years, which is so simple to state. Take a fluid, the simplest fluids, incompressible, inviscid, two-dimensional. Make it a linear shear flow so that the fluid goes to the right on the upper half, to the left on the lower half, and the velocity profile is linear. So you have this flow. Make a small perturbation and let the fluid go. Will it go to some rest, to some equilibrium, stationary state, or no? That simple question was open for since the time of when Kelvin, Rayleigh, Sommerfeld, and all worked on it more than 100 years ago, and was just solved last year by Bedrosian and Masmoudi, showing the important connection of this with the Landau damping problem, which we had solved with Moore. This is a third example. Plasmas, galaxies, fluids, solar systems, 4 systems which are very different physics, but same mathematical tools to answer some of the questions. Of course, some of the questions, but just a droplet in the ocean of what you would like to know to understand, for instance, the movie that we saw at the beginning of this talk. Thank you.
Okay, so time for a few questions. The first is that I couldn't help noticing in your slides one thing in common, which is that all the names were of men. So I wondered about the ladies. Have they done anything at all?
I hope so. It started with Newton. I could have mentioned, I could very well have added this. The French editor of Newton was Émilie du Châtelet, who was a very gifted mathematician and physicist, and she in fact improved the Newton manuscript. That was an early example. Of course, it is normal that in the old days, women were very few, because for a long time they were forbidden to study and to go to university. In some extreme cases, they were even killed if they tried to study. And so it was a logical consequence that there would be very few. Now times have changed, of course, and they are very strongly encouraged to go into these fields, all the more that we have a shortage, which is coming, of young people willing to take up these jobs of physicists, mathematicians, and so forth, hard science, so to speak. So times have changed, but it certainly takes time before this equilibrates. And anyway, what do we know about the tastes and the careers in which women will like to go and so forth?
So it kind of brings me on to my second question, which is sometimes I meet mathematicians and scientists who are well respected at the sort of top end of their career, and they don't want to go and talk to young people because they see that science or maths is a job in which you need to concentrate 100%. And sometimes they also don't want their students to go out and talk to the general public because they feel that they also should be spending time researching in the lab, writing papers, and not going out and doing anything else. And obviously you do that. You write books and you go into schools and you do lots of other things. And it's obvious to me what the impact of that would be on the people or the young people that hear you speak. But what impact does it have on you? And what would you say to those people who don't go out and do it?
To those people, I would say that in first approximation, they are right in the sense that it really takes up a lot of time for your research. Everything that is communication takes up a lot of time because you have to find the words, you have to go there in person, you have to spend time with them to increase the confidence and so on. It does take time. But there are other rewards. You feel so good after you have given this kind of speech to a crowd of young students. It really is nothing. It's much better than giving a talk to your colleagues. It really reinvigorates you. It shows you that you are being listened to, that people are of curiosity. It also helps you understand what you're doing, why you're doing it, why it comes in the story, in the history, and so forth.
Yeah, and I think it's also a tradition of ESOF that we want to create opportunities for the young scientists and the young people to have the experience and the interaction with the older people, the more experienced people. I think that's probably all we have time for, but I just wanted to thank you again on behalf of the audience, on behalf of the organisers of ESOF, for sharing your time with us today. It's much appreciated. Thank you very much.
Thank you very much.